We have been so far in this module looking at three main types of differential equations. We started our discussion with the wave equation in one dimension, and then we also saw the heat equation or diffusion equation. And then when you switch over to 2D Cartesian, so in here, that is for one dimension problem, obviously the domain is a straight line between x equal to a and x equal to b. And for two dimension Cartesian, you're going to have a rectangular region in general. So we'll call this x, we'll call this y. And let's say we have a domain which is like a rectangle, x equal to a comma x equal to a, y equal to b. This is a comma b, this is 0 comma 0. And then for cylindrical polar, generally speaking, you would have a z or an axial coordinate, a radial coordinate or a radial direction, and a perpendicular direction e theta. We'll see this more in vector calculus. But the idea is, if you have a purely radial equation, you have a domain that is in reality a circle, but we consider the region between r equal to, say, for example, r1 and r equal to r2. We saw problems or we saw examples of how you would deal with if r equal to 0 and the other end is just r equal to uppercase r, or an annular region where r equal to a and r equal to b. So what I want to emphasize now before I continue with today's topics is that in cylindrical polar, this is the complete equation or complete spatial terms that appear on the right side. How we get this is a matter of using vector algebra operators, which we will do as module 6. But for now, what I want you to understand is this symbol UR is shorthand for partial derivative with respect to R. So you can make the extension about other operations. So this is the right hand side, and in any given problem, you could have a combination of R and theta without any Z dependence, like an infinite length of a object, and you are considering only like a thin section or a thin plate. So this is usually called the thin approximation, so that you don't have to worry about Z or dependences on Z. And you could have a problem in which you have R and Z, but not theta, and that is the more commonly known axisymmetric approximation. Axisymmetric approximation. Rarely you have a case where you don't worry about the radial dependence, but weirdly care about the theta and Z. I don't know of such combinations, so I'm not going to go into that. But what we did last time was to deal with this particular equation. Do you recall? We derived the Bessel functions as the solution to the spatial part, and we derived cosine functions as the solution to the time part or the temporal part. While you do these problems, the first thing I want you to always do is to visualize the domain in which you are solving this equation. For example, if you are interested in, say, for example, this problem, heat UTT equal to C squared URR plus 1 over R UR. So our domain, let's say, is R equal to 0 and extends from there to R equal to R. This is really a circle. Okay, this is really a circle that you are dealing with, except you ignore the theta dependence, and it's not also not a cylinder by ignoring the Z dependence. So we got the solution for this. Cosine for the time and Bessel functions for the radial solution. This is all what we did last time. And if you go back to the solution we finally derived, it is of this form. U of r comma t am cos lambda mt plus bm sin lambda mt multiplied by J naught of alpha m over r multiplied by r. So your domain is a line, but when you have one of the points starting at 0, one of the automatic boundary condition is that the derivative of with respect to r must be 0 here. And on the other end, we considered the boundary condition u equal to 0. This is what we did last. Okay. And as initial conditions, we had u of r comma 0 equal to f of r and ut of r comma 0 equal to g of r, which was used to evaluate am and bm respectively. So this is to model radial transport without paying attention to axial or angular dependence. Okay. Suppose you consider this equation, or this one for that matter, instead of worrying about the angular dependence, you want to consider both radial and axial dependence. So we write our equation to be URR plus UR over R plus UZZ equal to 0. First, how would you draw the domain? You have both radial and axial directions. How do you draw the domain? Sorry? To be a cylinder with an axis of symmetry, suppose if you are considering a start at r equal to 0 and goes up to r equal to r, and this is say z equal to 0 and goes up to z equal to L. I mean, I've drawn this like a rectangle, but you can imagine this is part of a cylinder. Okay, so we can specify boundary conditions, but at this end, on the axis of symmetry, partial u over partial r is 0 along r equal to 0. Symmetry. Okay. And I'm going to solve a very specific problem where we are going to have boundary conditions u equal to 0 on the bottom face, u equal to 0 on the curved surface, and u equal to f of r on the top surface. This is the boundary condition for which I'm going to solve this problem. Okay. So this is Laplace equation in 2D cylindrical polar. Okay. What is, before we go into this, what is the other variant possible? That is, we talked about purely radial, that was last lecture. Now we are going to talk about the thin approximation. Sorry, we're going to talk about the axisymmetric approximation, which is that problem. What about the thin approximation? How would that equation look like? thin approximation is, sorry, the axis, thin approximation is, this is axisymmetric. The thin approximation would be URR plus 1 over R UR plus 1 over R squared U theta theta equal to 0. So this is Laplace equation. Again, in 2D, we just call this polar because there is only R and theta. How will the domain for this look like? This is the circle, a proper circle. And if we are considering the entire circle, starting at R equal to 0, to R equal to R, and the angle is measured from this direction, which is like a reference direction. This is for a circle, but you can also imagine the angular case, right? That is, if we draw a domain, which is two concentric circles, and our domain of interest is between this region. A less than or equal to R less than or equal to B. In this case, 0 less than R less than R. Let's talk about boundary conditions for this problem here. What are the boundary surfaces for this circle? So if your domain is this, what are the surfaces on which you can specify something from the outside? You can specify the value of the function or its derivative on the circumference. But what happens within is a result of the solution to the PD. Or if you want to talk like an experimenter, you can sit outside and set a value, but what happens within is the physics, right? So you can write U at R equal to R, comma theta is f of theta. Here, I want to write this here. U at R equal to R, comma theta is f of theta. You can also write U is analytic at R equal to 0 at this point. It has to be analytic. Okay. With these two pieces of information, you will have to derive a solution for U, which has to depend on both R and theta. Here U has to depend on R and Z, where 0 less than R less than R and 0 less than Z less than L. What about the annular case? I have A less than R less than B. I can 0 is not part of the solution. So I can say U of A comma theta is f of theta and U of B comma theta is G of theta. If your object or domain of interest and is a circle, a bounded region or a finite region, and you are interested in solutions in the within, that is within that domain, this would be the way to state the problem. Suppose you have a domain which is excluded by a circle and everything else in every direction is your domain, how do you define your domain? Suppose the same equation is applied in the space outside the shaded region. How is the domain? How to write the domain? R less than equal to R less than infinity. That is our domain. And you would specify either the flux, it could be a body that's radiating heat, or it could be a body at a constant temperature. So you could specify u of r comma theta equal to f of theta, and u has to attain some finite value in the limit of large radii. Those are your constraints. Okay. Also here, the way we have written this problem, this is for internal domain, meaning within a cylinder. You can also do the same problem or like the same equation, but the domain of interest being external domain being u of r comma z, r less than infinity, and it could be finite or it could also be finite in the z direction where you have 0 less than z less than L. So it's like a antenna or a charge that is placed at like a cylindrical shape, and you want the electrostatic field outside the charge. It would be a simulation of that type. The reason I'm presenting this today is to show you that there are many variations in which this Laplace equation, including the third term, the z term, could be used to model relevant physical phenomena. Not every, like you can keep coming up with different combinations or different types of domain, different types of dependencies, and so on. We are going to do this problem. I've worked out the solution. Hopefully we can go through this. Okay. I want you to try this problem. Try this. I'm going to try it as well. And this is where I wanted to show you something that I posted today. So I posted a handout on Canvas. This is the Cartesian Laplace equation in 2 dimensions. We went through this in class. It results in a single Fourier series right here. And what I've done is to work it out and post that steps for you with a specific set of boundary conditions. This is the boundary condition. What you should also take away is that every solution procedure will have quirks that are unique to a given set of boundary conditions. This is not universal, and every time the boundary conditions change, your approach has to take cognizance of that. That's one thing. The other is sometimes we bend over backwards to select boundary conditions that are really simple to make this separation of variables method to work. Or in other words, it has harsh restrictions on how it can be used, but it's physically very intuitive, and that's why we learn it. Okay? Once you have the solution in front of you as a function, there is a lot of analysis you could do with that. That's why we learn it in the first place. So this is Laplace equation in 2 dimensions with this boundary conditions. And then the wave equation in 2 dimensions. This is the one I kind of messed up. I redid that. And what you can see here is it is for boundary conditions of u equal to 0 on all sides, like as though you have a rectangular plate that you have clamped around the periphery, and you are displacing the plate, letting it go, and watching the vibration. That is what this problem is. This solution procedure is for a very specific set. Okay, don't put this on your cheat sheet and expect whenever you see this in the exam or something, don't put the same solution everywhere. With one change, make u equal to 1 on any one side, this whole procedure cannot be used. You will have to start again. Okay. So if you go through this, it results in a so-called double Fourier series. And what you have is this BMN, which depends on both m and n integers. And I also tried to explain how we can actually get this systematically without having to do patchwork, like memorizing any formula. And in the end, you have this long solution here, which depends on both cosine and sine, as well as sine terms that describe this problem. So I would like you to take a look at this and practice similar problems related to Cartesian coordinate system. Now coming to today's cylindrical coordinate system, the axisymmetric problem. Here's the ODE, here's the boundary conditions, and we're going to go through this. Okay. What I want you to do, not for credit, this is for your learning, is to, in a similar style, do the axisymmetric problem. Sorry, do the thin approximation problem, where you will have u, r, and theta, the one that's behind the board here. I want you to try those problems, and that is something. Did I bring my book today? Yeah. So if you go to problem set 12.10, boundary value problems, Dirichlet problem, Neumann problem. What you have there between as problem 4 and then later as problem 5 to 8, anything related to circular membrane up to problem 18 is basically this equation or the other equation with r and theta. So you could very well expect a problem in the exam where you have second derivative with respect to r, first derivative with respect to r, plus second derivative with respect to theta. You might expect that thin plate approximation problem in the exam. I'm just saying to scare you so that you will try this. Okay. All right. This I posted to Canvas, and similarly, I plan to write up something for the thin plate, the thin approximation, and also post it. Okay. All right. Let me stop sharing. Okay. So here we are. Where do we start all these problems? What's the first step? Say it again louder. Use a product of two functions, which are functions of r and z only. That is, you are saying u of r comma z is h of r times q of z. That is the first step, where you try to say that it is a product of two variables. Anybody want to question why is that true, or why should that be true? Is it true all the time, or is it only true in some cases? If you ask me, I don't have proof to say this will be true all the time. There might be functions in which r and z appear as products, say as part of a polynomial, and there might be no way to separate them into two separate functions. You could easily prove that by doing a CFD solution and then proving that it's correlated exactly with the product RZ and it can't be separated. Okay, so it's not that you can apply this for every problem in principle. You have to be selective about which tool you are going to use for a given problem. There is analytic solution which you can obtain using this approach. There is numerical solutions you can use using finite difference, finite element, finite volume techniques. Okay, so you have to be judicious about what you want to use. All right, so we have this. So URR plus 1 over R UR plus UZZ equal to 0. I'll write this d squared h over dr squared times q plus q over r dh over dr plus h times d squared q over dz squared equal to 0. I felt my presentation at least 2 lectures back was a little cluttered. So I'm trying to slow down and do this step by step, okay, so that I don't trip myself. So that would mean I can divide throughout by HQ. I would have 1 over H d squared h over dr squared plus 1 over r dh over dr equal to minus 1 over q d squared q over dz squared, and we'll say this is equal to some minus k squared. So you get two ordinary differential equations, one of which is d squared h over dr squared plus 1 over r dh over dr plus k squared h equal to 0 and d squared q over dz squared minus k squared q equal to 0. Okay. So if you take this equation, the first ODE, we have d squared h over dr squared plus 1 over r dh over dr plus k squared h equal to 0. We need to select boundary conditions for this equation. So on this surface, you have the derivative specified, and all other surfaces you have u value specified. So how will you tackle this? Sorry? It is the Bessel's equation. We are going to get there, but before we do that, I just want to write out the boundary conditions for this ODE. So if you look at this surface, the curved surface, you have u of r comma z equal to 0 or h of r comma q of z equal to 0, where z is actually varying between 0 to L. So if we make the general assumption that q of z is not, trivially 0, we could say this means h of r should be equal to 0. H of r must be equal to 0, and by similar reasoning, we can say partial u over partial r at r equal to 0 is 0, or partial over partial r h of r times q of z at r equal to 0 is 0, or we can write first derivative of r, first derivative with respect to r at r equal to 0 is 0. The more broader way of saying this is to say u has to be analytic at r equal to 0, which you will know we are going to later use to rule out the Bessel functions of second kind. So we apply the transformation S equal to KR, which means we are going to get d squared h over ds squared times k squared plus k squared over s dh over ds plus k squared h equal to 0. Assuming k squared is not 0 in general, we will get the Bessel's equation This is Bessel's equation with parameter nu equal to 0. As we saw last time, we know the solution to this h of s is j naught of s, or h of r is j naught of kr. Now we use the boundary condition h at the radius uppercase r is 0, or j naught of kr is 0. We did this last time also, but can somebody tell me what is the interpretation for this statement right here? J naught of kr is 0. What does that mean?
That's what we're finding for the roots of Bessel function.
So it's like saying k multiplied by r are the roots of the Bessel's function. Can be an endless sequence. But what we are interested in is to write r varies between 0 to r. Radius varies between 0 to uppercase r. So we are interested in 0 less than or equal to kr multiplied by kr. That is, all the values of kr, all the values of kr, uppercase r, that lead to j naught of kr equal to 0. And there could be multiple values. That's the point I'm trying to make, which is to write, if you plot k times r, the Bessel's function could cross the axis multiple times. So each value is a potential solution or a root. Okay. So we have h, which now depends on an integer m of r, equal to j naught of km, which I'll write alpha m over r multiplied by r. When r equal to r, h should go to 0. Or hm should go to 0. So So this is one piece of the puzzle like we saw last time. The main takeaway from this is K is no longer any real number. It follows a certain sequence, K1, K2, and so on, or I'll write alpha m over R. And there are only discretely many values of alpha that we'll consider, or discrete values of m that now will be considered. So if we pick out the other equation, which is here, I'll rewrite it here. D squared q over dz squared. K is no longer any real number. It is precisely km or alpha m over R squared times q equal to 0. You know this equation, which would mean q of z is going to be, say, C1 times exponent of alpha m over R multiplied by z plus C2 exponent of minus alpha m over R multiplied by z. We now need to figure out C1 and C2. One of the logical things that you should remember here is you can use a boundary condition only once. We have used up this, we have used up this, we have the other two, which we now have to use. Okay. So for this equation, what are our boundary conditions? U is 0 or U of R comma Z equal to 0 is 0. And that is like saying H of R multiplied by Q of Z equal to 0 is 0. You know what is H of R, and Bessel's function is not in general trivially 0. So we can pretty much say Q of 0 is 0. Q of 0 equal to 0 should imply C2 equal to minus C1, or Q of Z gets simplified as C1 hyperbolic sine of alpha m Z over R. And since this function depends on specific values of m, it would be meaningful to include the m dependence for q. So q is also now evaluated for discrete values of m, which if we now put together, u is now a function of m of r comma theta, which is, I'll write C1 J naught of alpha m R over R multiplied by hyperbolic sine alpha m Z over R. Sorry, theta um of R comma Z. So u in as a linear combination R comma Z is m running from 1 to infinity. Instead of calling it C1, I'll start calling it Cm because it depends on a specific value of m, J naught alpha m r over r multiplied by sine h alpha m z over r. What's the last thing that we have yet to use? We are yet to use. This is the only boundary condition which we haven't used yet, right? And if we write u of r comma z equal to L equal to a function of r only. That's what f of r is to denote. Then we can write f of r is summation m equals 1 to infinity Cm J naught of alpha m r over r sine h alpha m L over r. So if I consider an interval of for z, it is for r, 0 to r is Bessel function orthogonal in this interval. How do you prove this? So you'll have to integrate 0 to r, j, I call it, what letter haven't I used? Can we call it p and q? No. I and j. So let's say ji of r, I'll use I and k. Ji, I'll use jp and jq of r times 2 pi r dr. You'll have to prove that this integral is 0 if p is not equal to q. Okay, not in the exam, but if you are actually using it in your research or your work, and you are going to construct a solution, it's good practice for you to check if this function is actually orthogonal in the interest in the region that you are considering. Okay, you can do that, or we can do that, but we won't do that. What we are going to then write down is Cm, the coefficient, is 0 to r, J naught of alpha m r over r multiplied by f of r dr divided by 0 to r, J naught of alpha m r over r squared r dr. So there are identities involving Bessel functions which can be used to solve the integral in the denominator, which is given in the book. In the exam, if you are short of time, I would accept numerical solutions. But in general, you can actually get analytical expressions for the denominator. Okay, and even this, if f of r is a really simple function, like a constant, may not be a problem. But for more complicated functions, you might need to resort to numerical. So this expression here is meant for the internal solution. meaning internal solution for r less than the radius. Shall we now flip the script and try to get the external solution for the solution of the same problem with a cylinder in exactly the same location with the same geometry, but now we are interested in the solution outside the cylinder and not inside the cylinder.
Right in the beginning, say that the derivatives of h is equal to the derivatives of q, which is equal to negative k2. How do we know what sign for k2 should be used?
This one?
Yeah.
So this is this sign, you could actually get it to be like a positive sign, but what you will end up getting is an equation that is not any standard form. You will have to go through the Frobenius method to get the solution. If you go through the method, even that negative choice should again lead you back to Bessel functions. Because there will be a contradiction that you will encounter at some point which will make you to flip the sign. We just didn't take that path because we are not the first ones to do this, so we just took the path which we know will lead to the answer. But the other choice is no different from this choice. Should be no different from this. Your question is, how do I know when I'm dealing with a new equation which I've never seen before? The best answer I can come up with is to say, you'll have to try both. And odds are, in the first trial, you might pick with 50% chance the easier choice. Otherwise, you will anyway come back to the easier choice. That's what I would do. Is this clear? Like, able to follow? It's kind of a repeat of last lecture, but without the time domain, so that we can also pay attention to the spatial variation. Okay. But the pitfall here is, you shouldn't think that to this equation, if you also add a time dependence, like c squared, and this could be either ut or utt, the fallacy is you shouldn't think that this solution and the time can just be like slapped onto that. You'll have to go through the process from beginning. The only difference when you have both time and space is, first separate the variables as time and space. So you would write u of r comma z comma t is a function h which depends on r and z, and a function g which depends on t. So you will get a partial differential equation in space. Then you split that into two functions. That is what you can also see in the handout that I posted, which I did for Cartesian. It's basically a repeat of the derivation in the book. But if I put myself in your shoes, I just wrote down the steps that would actually need explanation so that you could see my thinking. Okay. So remember this. Okay, I won't, not a sadist to ask you this in the exam. Like, make you do 3 variables in the exam that can easily take you 1 hour or 1.5 hours. Okay, so we'll either stick to one spatial coordinate and one time coordinate, or 2 spatial coordinates. We won't do the other combinations. There are, in its full glory, you can do 3 spatial variables and 1 time. That's 4 variables. That's some serious derivation you need. Okay. So, coming back to this problem, now I want to get the solution in the external domain. Can you define the external domain? So the external domain would be R less than R less than infinity. Okay, and we would write U equal to, let's say U equal to some constant UA at R equal to R. So it's like a cylinder with a fixed temperature that is conducting heat in the radial and axial directions. If your cylinder is finite, okay, your cylinder is finite, you're going to run into a problem. What is that problem? Suppose your cylinder is finite, you will have some edge effects around the solution, around the edge. The solution will look different than the solution near the or far away from the edge. So that's why in your engineering analysis, most of the time we try to find excuses to say either your pipe is of infinite length or your fin is of infinite length, and ignore these edge effects. Edge effects are difficult because mathematically they can be quite challenging with or without separation of fields. Okay. So if you think about an infinite cylinder, this is R equal to R, and you have a constant value UA, and U has to be a finite value as R goes to infinity. That is the other constraint. So we are making another simplification to say ignore or ignoring edge effects to say UZZ is taken to be 0. That's one way to think about it, to say your gradients in the Z direction don't matter, or you can focus on a region that is reasonably far away from the edges and not worry about everywhere else, not worry about the entire domain. So whatever we are deriving is valid for a thin line or a plate that is far away from the edges. Okay. So if you write that, we haven't done this problem before, even though it looks like it's basically we are writing URR plus 1 over R UR equal to 0. But the domain is here, not inside. This is practically a ODE because it has only R in it, right? Can you write out the solution? So if you encounter something like this, what's the first thing you should do? Like a new equation, what will you do? You would try to see if it matches the template of any of the standard equations that we learned, which are, we learned Bessel's equation, we learned Legendre's equation, we learned Euler-Cauchy equation. We try to see if this will fit in with any of the known equations by setting nu equal to 0 or n equal to 1 or something, so that your problem is already solved. You just need to apply boundary conditions. So this would fit what template? Sorry? You want to do what, sorry?
We can write it d square of u plus 1 by r of t of u is equal to 0.
So you want to write this d over dr
Yes.
of ur and
double derivative of UR
okay
plus UR and derivative of UR.
plus UR
Sorry, 1 by R.
plus derivative of 1 over R.
No.
No, I'm not getting what you said.
Correct.
Okay, so you want to write this as partial derivative, like I would say, the derivative with respect to R of UR plus 1 over R of U. That's what you're saying?
This inside the
Actually, that was not the tangent I wanted to go on. This could be right, but we need time to check this. But what I wanted to say originally was, if you look at this equation and recall what is Euler-Cauchy equation, which is to write x squared y double prime plus xy prime times b of x plus c of x times y equal to 0. You divide throughout by x squared, that's one of the assumptions in this derivation, x over x squared. What we have here is the Euler-Cauchy equation with b of r equal to 1 and c of r equal to 0. This I will write, this equation is the Euler-Cauchy equation, or the one which we used to learn Frobenius method is the Euler-Cauchy equation. If you don't remember the name, it's the one with which we learned Frobenius method. Euler-Cauchy equation with P of r equal to 1 and C of r equal to 0. And B of r is supposed to be an infinite expansion B naught plus B1 r plus B2 r squared and so on. And this is C naught plus C1 r plus C2 r squared plus and so on. See, the whole idea of doing these first is that they are the template for many physical problems. So you don't have to keep repeating that exercise over and over. If you did this, you know the next step is to write the indicial equation, or the next step is to say the solution u of r is of the form r power, let's say r power nu summation m equal to 0 to infinity am r power n. That is the Frobenius method, or starting point of the Frobenius method, where nu and am have to be determined. And this next step is also will lead you to, for m equal to 0, okay, we assume a naught is not 0 and write the indicial equation r minus r times r minus 1 plus b naught r, or I should write nu times nu minus 1 plus b naught nu plus c naught equal to 0, where b naught is 1, c naught is 0. So you're going to get nu squared equal to, or nu squared equal to 0. That's correct. Right, nu squared equal to 0. Correct, just make sure. All right. So what are the three cases we saw in that situation? For nu, if you have nu1 and nu2, which are distinct, and nu1 equal to nu2 and nu1 minus nu2 is an integer. These are the three possibilities we saw. This is the easiest case. This is you can just obtain two linearly independent solutions very easily. This will lead to linearly dependent solutions. So you have to have one of them to be this value, and the other has to be a logarithm, something which can be looked up from the table. Same applies for the third scenario. So we are here, which is this scenario. So one of the solutions. Yeah.
Would it be easier if we treat this as a first order ODE? Because we can say UR is W and then it will be.
Yeah, you can do that, yeah. So what will we get there? We get dW over dr plus W over R equal to 0. Okay. So maybe this is not necessary then. I guess we'll again, like I said before, you'll get to the same thing. So what are you going to get here? Let's just go through this. This is dW over W equals minus dr over R. Or this is ln of W equal to ln of 1 over R plus an arbitrary constant. Okay. So you can use the first boundary condition to say okay, so how will we get C here? WR is, sorry, come again. No, we have boundary conditions for U and not W. So we need to first get back to U. So wait, hold on. So you have URR plus UR over R equal to 0. We are saying W equal to UR, which means we get WR plus W over R equal to 0, or dW over W plus dr over R equal to 0. And we have logarithm of W times R equal to constant, or W equals constant times R. W equals constant times R, and W itself is du over dr is constant times R, call it C1. So U of R is C1 ln R plus C2. So first boundary condition to say UA equal to C1 ln R plus C2. And how do you apply the second boundary condition? So then you get like a trivial solution. So this approach is giving us the trivial solution, which is physically useless. So that's why we want to use the other approach to get, you're going to get one solution, which is just this series. And then how would you construct the other solution? So nu is 0, that is one of the solutions, right? So U1 of R is simply m equals 0 to infinity am R power m. This is the solution to the ODE. Which ODE? Let's keep that in mind. URR plus UR over R. This approach we have tried and it leads to trivial solutions, so we'll set it aside. Substitute this here. If this is U1, what is U1 prime of R summation M equals 1 to infinity M AM R power M minus 1. And then U1 double prime of R is summation M equals 2 to infinity M times M minus 1 AM R power M minus 2. So you need to substitute these back in here, right? So what is URR? This one, sigma M equals 2 to infinity M times M minus 1 AM R power M minus 2, and then the other term is plus 1 over R summation 1 to infinity M AM R power M minus 1 equal to 0. The final result is actually much simpler if you go through the steps. I want to do that. One of the assumptions that we made initially is to say A naught is not 0. Okay, this series cannot have A naught to be 0, everything else could be 0. Let's consider the powers of R starting with starting with R power 0. I want to collect the coefficients of R power 0. Okay, R power 0. This 1 over R, I'll write it as M minus 2. Okay, so to collect the powers of R power 0, I need to set M equals 2 here. So 2 times 2 minus 1 times A2 plus, here I have to set M equals 2 again, plus 2 times A2 equal to 0, or essentially A2 times 4 equal to 0, which is possible only if A2 is 0. It's possible only if A2 is 0. What about R power 1? I have to set M equals 3. I have to set M equals 2 here. So I'm going to get 3 times 2 times A3 plus 2 times A2 equal to 0. Since A2 is 0, obviously A3 also has to be 0, which means successive values are all 0. Okay. What about A naught and A1? So U1 of R is A naught plus A1 R. Okay. What about the other solution? We took nu equal to 0, so we can't use nu again. We need to look up the other solution U2. U2 of R. Can you look it up? I think you need to go back to chapter 5. Chapter 5, theorem 2, page 182, 183. chapter 5, theorem 2, pages 182 and 183. And we are interested in the second case where we have a double root. So we figured out one of the bases to be this, okay? And the second basis function, u2 of r would be u1 of r times natural log of r plus, in our case, nu is 0, so we won't have that, plus a1r plus a2r squared plus and so on up to infinity. So our u2 prime of r is u1 prime of r times ln r plus u1 of r divided by r, and then you have the infinite series, which is, this is nothing but sigma am r power m, r equal to 1 to infinity. So this would be m r power m minus 1 r equal to 1 to infinity. u2 double prime of r, this will be u1 double prime of r times ln r plus u1 prime of r divided by r plus u1 prime of r divided by r minus u1 over r squared. Plus m equals 2 to infinity m times m minus 1 am r power m minus 2. Do you see any simplification possible here? If this is your u1, where is your u? Yeah, if this is your u1, u1 prime, double prime of r should be equal to 0. Let's want you to try this or complete this, and I'll try to complete this and post the handout. So this problem, as well as the other problem on partial u or urr plus 1 over r ur plus u theta theta over r squared equal to 0, where you get a boundary condition like u of r comma theta equal to f of theta. This is a very important problem in elasticity theory, in heat transfer, in conduction heat transfer, and many other electrostatics or viscous flow. So please try this at home, okay? And you complete this, I'll complete this and post the handout. We'll stop here. Next lecture, I want to start spherical polar coordinates, and that would pretty much wrap up this unit. And I think I would have one more lecture on Thursday, in which I want to do examples. So it would be better if you try something before and come to me with like suggestions, okay, for next Thursday. Yeah. So tomorrow 10 o'clock? Yeah. Do you have any